I'm very happy to be here at AIAA to talk to you about a subject that I'm passionate about, not just AI in space, but also how AI is essential to solve one of the biggest questions that I think humanity faces, which is, are we alone? And so I'll start out with a little bit of giving you a background on how we're using AI now, and then I'll talk about how we need to use AI, in fact, to hunt for life beyond Earth. So this is actually stuff from EO1. Okay, so this is actually from EO1, which is now several decades ago. We had AI flying in Earth orbit. In fact, this is the first machine learning that was flown in space in 2004. And what this does is this enables the spacecraft to determine what it's looking at and send text messages. So the catchphrase here is we want to send knowledge, not data, right? So things like this volcano is erupting. And then we actually network this together with lots of other satellites, and this is very apropos. This is very apropos because right now as we speak, my poor family is evacuated from their house in California, escaping wildfires. And so one satellite might notice that there's a thermal emission, that there's a wildfire, and then we have this integrated system where we can task other spacecraft on the basis of that alert. So what we call this is multiple smart software agents representing the spacecraft. And again, as I said, this is the first flight of machine learning in space in 2004. And there we were flying support vector machines. Now, of course, the rage is deep learning. And sadly, this EO1 spacecraft ran out of fuel, eventually stopped operations in 2017. But you don't have to feel sorry for us because we moved on to bigger and better things with the Mars rovers. And the Mars rovers have quite a bit of AI on them. First of all, they have AI that helps them to drive around and avoid obstacles. They also have this system called Aegis, which does autonomous targeting. That used to be they would take some images and they would download them to the ground. The scientists would figure out what are the interesting rocks, and then they would target those, upload a program to target those rocks. Now the rover does that all autonomously. They give it certain science criteria, and it hunts for targets that meet those criteria, and then it zaps them with this laser-induced breakdown spectrometer, and that's to get underneath the weathering, and that tells them about the composition and geology of the rocks. And so this is actually showing some of the, in fact, the targets that are found. And the system is so effective that there's a significant uptick in the number of these measurements they take. The other place that AI is being used all around JPL and NASA is in mission planning and scheduling. And so these are just a few of the space missions that are using this. So in the upper left, EcoStress is measuring plant stress all around the world. All of the observations are scheduled by AI software. In the middle, OCO3 is the world's premier CO2 retrieval instrument, and its observations are, again, all scheduled by an AI system. And then if you stop by, this is a shameless plug, the JPL booth, we'll show you the model of NISAR, which is a radar mission that's going to launch early this year, actually. That's a joint mission between NASA and the Indian Space Agency, and that mission was designed and will be operated using, again, our advanced scheduling system. These are just some of the data from EcoStress and from OCO3 that were scheduled and acquired with our software. Now, all of you now probably think of AI as just machine learning, so I'll cater to all of you now and talk about some of the ways that we use machine learning. So how do we use machine learning? Decades ago, for decades we've been using machine learning. This is machine learning categorizing the second Mount Palomar sky survey. So it's characterizing all of these fuzzy images into galaxies, artifacts, planets, satellites, whatever. And it's actually better than humans at classifying this because it doesn't, it needs as high quality images. So literally decades ago we were doing this, and we're still doing this. This is from the transient factories, both the Intermediate Palomar Transient Factory and the Zwicky Transient Factory, and this is joint work with Caltech and George Drogovsky. And we're also even doing this not just in the visual domain, this is in the radio astronomy domain. And what we do is we triage vast amounts of data, and then that data is then handed on, the best matches are handed on to the scientists for finding different things. And then Deep learning, which is all the rage now, we're using this all over the place to index large amounts of data. This is MSL data, this is MRO, Mars Reconnaissance Orbiter data, and it's automatically classified using deep learning techniques, so convolutional neural networks, so that the users can say things like, I want to see images of Swiss cheese. This is a particular kind of geological formation, and it'll drive them to the images that have that data set. So what's better than actually indexing based on the images themselves? Well, imaging based on what scientists say about the images themselves. So most of the people in the audience have probably used ChatGPT and other LLMs. That actually uses as an underlying technology this thing called BERT NLP. That's how it tokenizes the streams. This is work by Kiri Wagstaff, and we applied this to scientific papers. And what we learn is we learn the correlations between concepts, relationships, and other concepts. So what that means is I can type into the Mars Target Encyclopedia and say hematite. So hematite is a mineral that forms in the presence of water, and it will drive me to these data sets. Whoops. It will drive me to these data sets, the green dots, where somebody has published a paper that uses the word hematite close to a mention of that data set. Okay? And so we're literally indexing the world's scientific knowledge and helping scientists use that. And so earlier on, I talked about this fire sensor web that we used on Earth to try and link together all these, network together all these different sensors. We want to do that at Mars. And again, Kiri's team was doing the start of this. We're not yet there yet, but just the start. And why would we want a sensor web on Mars? Well, it turns out Mars is constantly having impact craters. What does that mean? A meteorite hits the surface of Mars. And the Mars scientists are very interested in this because it exposes the underlying geology. But you have a short window to then image that geology before all the dust storms happen and all the images you've seen of Mars are all reddish. That's because this iron oxide dust is everywhere. So here, the sensor web takes detections of fresh impact cratering with the Mars CTX, MRO, high-rise CTX camera, which takes big images, wide field of view, but not super high resolution. And then when we see the fresh impact crater, you zoom in on it and you try and take a CRISM image, which is a hyperspectral instrument that you can study the underlying geology. Okay? And so now I talked a little bit about where we are, and now I'm going to talk about where we're going. So sadly, the scheduling worked out that if you actually want to hear about CADRE, which is our multi-rover mission to the moon that's going late this year, you should have been here about an hour ago. So I won't say too much about that, but I mean, there's a website on it, and it's 3 rovers plus a lander, and they use AI to coordinate the rovers to either map out areas faster or to take joint measurements with a ground-penetrating radar. And the rovers have to turn themselves on and off to manage their thermal state, and so it's actually one of our planners that's on board the rovers that helps it to do that. But if we want to hunt out life, I promised you hunt for life, we have to go to more and more exotic locations. There is a robot called EELS that's developed at JPL. Masahiro Ono is the PI. And this is a snake-like robot that's designed to go down crevasses, like on Enceladus, which is one of the moons of Saturn, in order to hunt for life. And I say snake-like because it does things that no snake can do. It will go down a crevasse and straddle the crevasse, pressing outward for grip. I know of no snake that can do that. But this is a next generation of explorer that really has to rely on AI. It has to balance. So I'm a decision theory guy. Decision theory is basically utility and probability. Utility is a way of saying, I really want to do that, or I just sort of want to do that. And probability is how likely that outcome is. So this snake robot needs to say, if I'm wandering here and I know where I am now, I can go faster and I don't have to sense a lot. But if I'm over here and I don't know where I am and there's this narrower gap, I need to go slower and sense more. And then when I'm over here, it's low risk, so now I go faster. So it needs to balance risk and reward. And so this is a completely different kind of AI and autonomy. We're not just trying to do things better and faster. We're trying to really understand that's the interesting science as a proxy for the scientist, which sadly we can't send the scientist to Saturn. And this is just some fun stuff about, you know, with this snake, you can actually go all kinds of places. Whoops. And I don't know why that video is not playing, but the snake can go sideways, it can go sideways up hills, all kinds of very fascinating robotics things. So now, I want to make sure that I have time for questions at the end. I'm really going to go out there and stretch your imagination. So scientists are really obsessed with two locations in the solar system as potentially harboring life. One is Europa, which is one of the moons of Jupiter. Arthur C. Clarke in 2001 notwithstanding, we don't listen to science fiction authors, so we will not stay away from Europa. Europa has more water than Earth, and so water is known to be very important to life. That's why we want to go there. We have the first mission, Europa Clipper, which just launched last fall, which will fly by Europa and take remote sensing measurements. The next mission, Beyond Clipper, which is just a mission concept at this point, would land on the surface, would only survive about 30 days before the radiation would kill it and it would run out of power. And by the way, half of those 30 days it can't talk to the Earth because Europa is screaming around Jupiter every 3.5 days. It's crazy. And Jupiter, since it's a failed star, it's producing all this RF interference. So it's a very different situation from how we operate the Mars rovers. When the humans go to sleep, or we can't talk to it for 1 3/4 days, the lander keeps operating. So we have to operate with the lander in a very different way. When we did design simulations of this, we explained it to the scientists. You have to tell us the next sample, because by the time you get to command the lander, it's probably already 2 or 3 samples ahead. And this is quite a challenge because, again, the lander has to understand uncertainty because the batteries could die at any time, the radiation could kill it at any time. It doesn't know how long it's going to take to trench. It has to know if it's trenching and if the going is really slow, maybe it should switch over to another location. It has to be able to evaluate science sites as this one is a better one than this one, at least make a guess, because otherwise you might wait for 2 days, and that's like 8% of your lifetime that you just spent waiting for the humans to tell you, dig there and not there. So we want to go there because there's all this interesting stuff. We know that there's CO2 at Europa, all these interesting things. And this is actually a robot prototype that we took to the Matanuska Glacier. Some of you might have been there in Alaska and demonstrated it for 3 weeks doing exactly these kinds of things. Again, decision theoretic planning, we have to balance risk, reward, and likelihoods all the time. But what would be the next mission to Europa? As I said, there's more water on Europa than Earth. Why is that? Because this ocean, which is underneath an ice cap, is 10 or more kilometers deep. And that's really deep. A 10-kilometer deep ocean on the Earth, think about it, that's like 35,000 feet deep. The deepest places are what? Marianas Trench is, I think, 39,000 feet. So there's more water there than there is on Earth. And some people even believe that there are hydrothermal vents caused by the gravity of Jupiter, which is so immense. And so the different forms of life have been found on Earth at hydrothermal vents. One of the beautiful things about science is it can be wrong and it can correct itself. When I was a kid, they thought life couldn't exist without photosynthesis. Now we know there's all kinds of life at hydrothermal vents that lives without any photosynthesis. So maybe there could be life there. But that's a hard mission. And this is a very old video that kind of tells you how hard it is. So first we have to fly to Jupiter, which takes a long time, and then there's all this radiation. And then we have to land on the surface, and then we have to melt through the ice cap. Did I mention the ice cap is kilometers thick? It might take a year or more just to melt through the ice cap. But the next mission past the lander is what we call Europa submersible. And the Europa submersible would have a base station. It would have to go out and explore and come back to the base station because that's the only way it can communicate to Earth. And as we jokingly say, if you find life and you don't communicate it back to Earth, you get 0 credit. Okay? So this might sound like science fiction, and it kind of is, but it kind of is not. In collaboration with the Woods Hole Oceanographic Institute and Chris German, the world-famous hydrothermal vent hunter, and Mike Chikuba, also a world-famous hydrothermal vent hunter, we've now made not one, but 2 expeditions to the Jurassic Massif. The Jurassic Massif is about 100 kilometers from the North Pole, and it is the only place on Earth where we know we have hydrothermal vents underneath ice. And what did we do there? We study the humans who actually control this robot called NUI, Nereid Under Ice, and they actually go there and explore the hydrothermal vents, hunt for the hydrothermal vents, and we build AI systems that replicate the same methods that they use to search for hydrothermal vents. There's papers on this. It's called nested search. And then we have other systems that are trying to mimic some of the astrobiology hunting signatures. But if you feel like I didn't get quite far out there enough, I'm going to go even further. You think that's hard? The real mission is to hunt for life at another star system. Okay? So the nearest star to us is Proxima Centauri. It's actually a binary system. Not super exciting because those are very hard for life. Better would be TRAPPIST. TRAPPIST is on the order of 10 light years away. But even Proxima Centauri, some of my friends who are in this area claim that very optimistically it would take 70 years to get there. Let's imagine the spacecraft gets there. How does it run its mission? Well, you could tell it what to do. It could tell you I saw something, and it could send you a message, and you could wait 4.5 years to get that message, and then you could tell it, oh, that sounds good, look there, and it could wait another 4.5 years. That's nuts, right? So to me, that's the AI challenge. It has to run a whole space mission on its own. What are the planets like? Which one is the interesting one to get into orbit around? What data does it send back? Because you're not telling it what data to send back, because again, it's got a 4.5 year lag or 9 years. And if it's TRAPPIST, it's closer to 20 years round trip. So to me, that's the ultimate challenge of AI in space. But we actually even have projects on that, how you would cluster the data, what's models of interestingness, and so on. And so I'll leave you with the JPL mantra, dare mighty things. I unfortunately missed it, but I understand that Lori Leshin, our illustrious lab director, in her opening speech on Monday said, we have to still be willing to do the hard things. And I'm not sure what's harder than going to Europa or Proxima Centauri to find life. So I have a little bit of time for questions. I'm happy to take questions. I will say, if you want a question, we don't have another mic, so you probably need to run up here and I need to hand you the mic, or I can repeat your question. So, questions? Comments? Can you come up? And other people who are interested, please just come up and queue up, because we only have a few minutes.
I was just wondering if you did any comparisons between using humans to look for the hydrothermal vents versus a fish or something that lives in that kind of environment.
Okay, so that's a great question. So she's basically asking, why did we take human experts as the gold standard for hunting for hydrothermal vents and not fish or something like that? That's probably a better question for Chris German than me, but I'm not sure we know how the animals necessarily search for their prey. The closest thing would probably be in the deep ocean searching for prey. I'm willing to bet that they do something very close to this nested search. So basically, nested search is a very simple concept. You do like a lawnmower or a search pattern until you detect a signal, and then you assume that the signal is stationary. Of course, it's not. And then you do orthogonal transects to try and locate it, and then you try and follow up it. You basically chase the chemical trail. And there are some other details that I'm not really getting into because the search actually happens in 3D. You do the nested search in 2D, but you actually yo-yo in the vertical dimension because if you have ever seen a volcanic plume from the side, it goes like this. It has what's called the plume injection height, and then it stabilizes at a particular altitude. And so depending on if you're in the terminal guidance or searching for the outer plume, you're actually guessing at the z-axis. So I hope I answered that question. Other questions? Come on, don't be shy.
Something like the snake robot that you talked about, where it's moving in a strange way in hard to predict environments. How do you train or otherwise create the AI for that, the decision-making process?
Great question. So I'm going to start out by a disclaimer. I'm not a robotics person, but my understanding of the control mechanisms on EELS is that none of them are learned. So they're all classical control, and there are specific policies that it uses for its locomotion. And it's not solving the full multi-dimensional problem because it's some crazy 40 degree of freedom robot, because every joint has multiple degrees of freedom and it has all of the joints. So it has specific locomotion behaviors and it switches from mode to mode depending on the gate, the goal and the gate. And the AI that I was talking about is what we worked on, not because that's the most important, but because that's what I know about. And that's the high-level system autonomy where it balances the risk and reward, where it decides, let's say, that sample over there is what I'm really interested in because it's a certain greenish streak, and it might be sulfur, and that's an astrobiology signature. Okay, but I would encourage you, if you Google Masahiro Ono, or Ronan Thakur. Actually, if you, I think it's eels.jpl.nasa.gov. They have like a whole bunch of papers on that, including on the controls part. Thank you very much for your attention. And like I said, come ask me questions afterwards if you have questions.
Oh, thanks very much, Steve.